Good afternoon. Here we are starting lecture 8 of Power Electronics and EV Drives course. In the last class, we completed rectifiers and we also worked out some numerical examples on battery charging technique using rectifier. So as I mentioned earlier, today we are going to start on AC to AC converters. So if you look at AC to AC converters, there are two different types of AC to AC converters. One is AC voltage controller. In AC voltage controller, you would not be able to change the frequency. Rather, you would be able to change only the magnitude. So RMS output can be changed. That is what is AC voltage controllers functioning. The second one, which is known as cycloconverter. Cycloconverter allows you to change the voltage as well as frequency, and it can change from three-phase to single phase to three-phase, and so on. So there are multiple types of converters that are available. So you can have single phase to three-phase, or three-phase to single phase, or single phase to single phase, or three-phase to three-phase. All these types are available in cycloconverter, and you would be able to change the voltage magnitude as well as frequency. Both can be changed using a cycloconverter, but we are not going to really look at the cycloconverter in this particular course because it's not generally used in electric vehicles much. It is mainly used in large capacity synchronous motor drives, where in industry, if you want to control the speed of a large capacity synchronous motor drive, then you might use, especially if you want to run it at a very low speed, you might try to bring down the frequency from 50 hertz to 25 hertz, or 20 hertz or 10 hertz or whatever. That can be easily done. So stepping down the frequency or bringing down the frequency can easily be done in a synchronous motor drive. Okay. So AC voltage controller is the one which we are going to discuss, and that is also quite briefly in this particular course, because again, the application of AC voltage controller is pretty much limited, especially in EV domain. Okay. So let me start with AC voltage controller. So AC voltage controller primarily has some niche applications. So the specific applications that we see for AC voltage controller are, one is wherever you have stadiums and we have floodlights, the floodlight intensity control can be done. So control of floodlights can be done using AC voltage controller. Another major application of AC voltage controller is also, especially single phase case, what you see as the electronic regulator for the fan. So that is basically an AC voltage controller. So whatever is sold as electronic regulator for the fan, ceiling fans and things like that, those are generally single phase AC voltage controller. Another major application for the AC voltage controller can be in the airport. If you look at runway lighting, so runway lighting in the airport, you might see that depending upon the foggy conditions or the weather conditions, It can have very high intensity light, or you might decrease the intensity of the light in the runway. Those things are again done with the help of AC voltage controller. And another application is the three-phase case. You might see that induction motors, which are three-phase induction motors, if you want to have a soft start, rather than applying full voltage and the motor drawing a very large current, if you don't mind having a lower torque during starting of an induction motor, for example, for a fan or centrifugal pump, where you are going to have generally load torque demand from these things. So the load torque that is demanded in these things, they are proportional to speed square. So if we are going to have a low speed during starting, you would see normally that the demand of torque is also very small in the fan or centrifugal pump, because it depends upon how much of fluid or how much of air it is displacing. The higher the speed, the more will be the wind or fluid it is displacing. So that is why generally the load torque is going to be proportional to speed square. So if I don't want really a large load torque during starting condition, then a lower voltage would do the job. So in those cases, rather than applying full voltage, you might like to apply only a limited amount of voltage, which will automatically reduce the current drawn as well. So in those cases, soft start is used. Um, so you can have, in fact, if you want to only vary the RMS value of the voltage, but you don't want to really vary the frequency. Frequency is a constant. Typically, a transformer can do this job. But in transformer, one thing is you have copper coils, you have iron core. So iron and copper, the cost is increasing tremendously. So although the transformer could do this job, it is very expensive as compared to AC voltage controller. AC voltage controller is just made up of semiconductor devices, and semiconductor device, the cost is decreasing. So you can see in general, AC voltage controllers cost is much less as compared to a transformer, because it is an electromagnetic device consisting of iron and copper as its material which make the transformer ultimately. So here the cost is higher. So that is one reason why instead of transformer, we can use an AC voltage controller. Another thing, this is the advantage in terms of using an AC voltage controller, but disadvantage is what we normally do is, if this is the total sinusoidal voltage that we want to apply, but we want to control the amount of voltage that is being applied, then you may apply only this portion of the sinusoid and similarly this portion of the sinusoid during the negative half cycle. So what you're applying is no more a sinusoidal voltage. That is the reason why you see lot of harmonics in the output of AC voltage controller. So in that sense, the motor can make a lot of noise when you are trying to run it at lower speed, because only part of the sinusoidal voltage is being applied. And that is one reason why you can say, AC voltage controller is not as, harmless as the transformer. Transformer is going to reproduce only the sinusoidal voltage exactly at a lower magnitude. If you are having N1 by N2, the turns ratio accordingly set up. But that is not the case with respect to AC voltage controller. So having said that, now let us try to look at how the AC voltage controller works. So let's start with single phase AC voltage controller. So in single phase AC voltage controller, what we are looking at is, you have an AC voltage whose magnitude needs to be varied before being applied to the load. So you are going to have two thyristors connected somewhat like this. This is how they are going to be connected. So let me call this as T1 and this as T2. So T1 will be able to conduct during positive half cycle if I call this as the positive terminal during the positive half cycle, and here is the load that is being connected. And T2 is going to be, game for conducting during the negative half cycle, provided a gate pulse is given at appropriate instant. So this is the arrangement for the AC voltage controller. So T1 conducts during positive half cycle. It can conduct during positive half cycle. And T2 will conduct during negative half cycle. So these are basically this is the arrangement. When you have two specific thyristors, you are as an individual thyristors, you are connecting them in anti-parallel. Rather than this, you may have a device called triac, which is consisting of two SCRs connected in anti-parallel configuration. So generally, these triac, you are going to have something like this. You have one triangle in this way. There is another triangle in this way. And then the symbol is going to be somewhat like this. So these are the two terminals. One is called MT1. The other one is called MT2. And the third one is called gate. So you are going to give a positive pulse to the gate during positive half cycle so that the forward thyristor or MT1 becomes the anode and it conducts. And you are going to give another gate signal during the reverse half cycle such that MT2 becomes the anode and conduction takes place in the opposite direction. So this is the symbol of the triac. Now, if I am looking at the sinusoidal voltage that is given from the supply side somewhat like this. So this is omega t, and let us call this as Vs. So what we have shown here is Vs. Now we are going to fire probably T1 at a firing angle alpha, which is away from 0 degrees. So this is delay angle. What we have had here is alpha. And T2 should be fired symmetrically at pi plus alpha. So in that case, what happens is I'm going to have this as the voltage starting point, and it is going to come like this. And if it is a resistive load, it will come until here, and there will be 0 voltage output from here. And again, this is going to be my output voltage. So this is going to be V0. What I see as V0 is here across the load. So this is going to be V0. So if it is resistive load, I can calculate from alpha until pi Vm square sine square omega t averaged over pi d omega t square root of this. RMS we calculate like this. Whatever is the waveform, we are going to square it and integrate it between the two limits, that is alpha to pi. And then we are going to calculate square root of that average over pi. This is what is the RMS value. So this is going to be V0 RMS. This is for R load. If I am talking about a resistance load, this is what is going to happen. Now in this particular case, we would be able to write this as Vm square divided by pi. And I can write sine square omega t as 1 minus cos 2 omega t divided by 2. So that 2 also I am taking it on this side. And this has to be integrated over d omega t. The limits will be alpha to pi. And we have to take the square root of this whole power half. So this would come out to be Vm square divided by 2 pi. And when you integrate 1, that is going to be d omega t is omega t. So we will have pi minus alpha. And cos 2 omega t is going to be sine 2 omega t. So it is minus sine 2 omega t. So it will be minus sine 2 pi, which is 0, minus sine 2 alpha divided by 2. Okay, so this is going to be the integrated value, and square root of this, that is going to be the actual value of this particular output RMS value. So this can be written as Vm. And if this 2 we take outside, so this will be Vm divided by 2 multiplied by 2 pi minus 2 alpha minus sine 2 alpha. And this entire thing divided by pi square. This is going to be the RMS value of the output voltage. So what you get as the output is very clearly a function of alpha. Depending upon what is the kind of firing angle we are choosing, that is going to either increase or decrease our overall, the output what you get. So if we are looking at it, we are essentially, so this is the expression for resistive load. When we talk about resistive load, this is going to be the output voltage. Whereas if we are looking at, so this RMS value is a function of whatever is the firing angle, as I told you earlier. Rather than resistance, if I have RL load, instead of resistance, if I have RL load, then what happens is, let me again draw the waveform. So let us say I have my sinusoidal voltage somewhat like this. This is the sinusoidal voltage, which is source voltage. Now, if I am again firing at alpha, and let us say this is fired at pi plus alpha. T1 is fired at alpha and T2 is fired at pi plus alpha. Now, what will happen is, in an inductance, you can't expect the current to abruptly rise to a large value. We are going to have again Vm sine omega t is equal to Ri plus L di by dt. The same equation is valid, just like what we said in the case of rectifier. So the current will increase slowly, and it will reach a peak at some point where Vm sine omega t equal to Ri. And after that, the current will start coming down. And it may not come down at pi. At pi, it will not come down to 0. So it comes down to 0 at some other angle beta. This is where the current comes down. So until then, until beta, T1 is going to conduct because the current flows in this particular direction. And after that, at pi plus alpha, we are firing T2. So the current has to start flowing in the opposite direction. So the current is going to rather start increasing again like this. And by the time it comes down to 0, it may be pi plus beta. So T2 will be conducting until this portion. So this here T2 conducts until this point, and T1 conducts from here until this point. So what we look upon as the voltage in this particular case is going to be, this is going to come up as the voltage, what I show as the shaded portion until here. So until T1 conducts, we are going to get this voltage. And for some time, the voltage is going to be 0. And when T2 conducts, we are going to have this as the voltage. And this will come up until here. The same thing would have happened in the previous cycle as well. So this is the way generally you are going to see the voltage appear. So in this particular case, if I want to really calculate what is V naught RMS, I have to integrate from alpha to beta and I have to average it over pi, and it should be Vm square sine square omega t d omega t, and I have to look at the square root of this as the RMS value of the output voltage. So in this particular case, it heavily depends upon how much are the relative values of R and L. If inductance is very, very high, and if you are going to have the power factor angle, let us say tan inverse of omega L divided by R, if I may call this as the power factor angle phi, if phi is less than alpha, that is, if I'm going to have the delay angle greater than this particular power factor angle. So if I'm going to have, for example, this is the sinusoidal input voltage, and I'm assuming that I'm going to give a firing angle of alpha here. But I have a highly inductive load. What will happen is, even if I'm going to start my current from here, it will probably continue beyond pi plus alpha also. Even if it is pi plus alpha here, the current might continue beyond pi plus alpha, which means T1 will keep conducting until this point. Then you are firing T2 at this point, automatically T2 will start taking over at this point. So there is no break in terms of the current at all. The current is continuous. So there is no break in the output voltage. So only if phi is less than alpha, then the output voltage is controllable, because there will be a break in the current. Otherwise, we are not going to have any break in the current at all. The current is going to be continuous. It will be in the positive half cycle. From there, it will come to zero, and then it will transition to negative half cycle in the other side. So you are not going to see any break in the output voltage at all. So only if the power factor angle is less than alpha, the output voltage is controllable. Otherwise, the output voltage is not controllable at all. So let me show you some simulation results, what I have done for the AC voltage controller. You can see that this is for a firing angle which is 60 degrees. So alpha is 60 degrees and it is a pure resistive load. So whenever we are going to look at the pure resistive load, the current is actually going to follow the voltage itself. So I've taken a resistance of 2 ohms. That's why compared to voltage, the current is just half that value. V divided by R is I. So you can see that the current is actually half that original value. The red color one is the source voltage. The blue color one is the load voltage. And the brown color one is the current. So you can see that the current is until pi, and after pi, the current becomes zero. So also is the output voltage. And then again, during the negative half cycle at pi plus alpha, it starts conducting. So the current is also coming into the negative half cycle, and the voltage is also exactly following the current waveform itself, or the source voltage waveform itself. So obviously you are going to have zero voltage interval here, here, and here, and so on. So from alpha until pi, you have to integrate the voltage to get the output RMS value. Whereas if you have an RL load, in RL load case, what happens is you are having at alpha the same firing angle, you are firing the thyristor number 1, T1, and you can see that the current is continuing beyond pi also. It is going until some beta. So this is pi, whereas this is beta. So the current is going until beta. That is the reason why you can see the voltage also spilling over at the output in the negative half cycle. Even during the negative half cycle, this voltage appears. And after that, there is a zero voltage period. And at pi plus alpha, that is 180 plus 60, 240 degrees, the next thyristor is fired. And you can see the current starts increasing in the negative direction. And it continues even beyond 2 pi. So it goes until 2 pi plus beta, or here it was pi plus, it was beta, here it is pi plus beta. So until here the current continues, and that's why the voltage is spilling over to the positive half cycle as well. And here is the zero voltage situation. So this is like what we talked about while discussing the waveform. You can very clearly see that the current waveform here also is spilling beyond pi. And that is the reason why this portion of the output voltage, which is actually coming into the negative half cycle, that is also available when you look at the load voltage. So the bottom line is, as long as you have a pure resistive load, you would be able to calculate the exact value of, whatever is the value of output voltage in terms of RMS. But if it is RL load, it is very difficult to compute what is this beta value. So it's not easy to compute the output RMS value. All we can say is, the output voltage can be controlled only if the power factor angle is less than alpha, or the delay angle. Otherwise, you are going to see continuous conduction, and that is definitely not going to allow you to control the output voltage. Okay. So the next thing that we are going to see is three-phase AC voltage controller. So the three-phase AC voltage controller comes in many configurations, but I'm going to discuss only one particular configuration here in this particular course. So let us say this is A phase voltage, this is B phase voltage, and this is C phase voltage, and I'm taking up star connected source. So this is, let us say, VAN, this is going to be VBN, and this is going to be VCN, each of the phase voltages, and this is the neutral. Now from here, we are going to have the AC voltage controller in A phase somewhat like this. So it could be replaced by a single triac. And similarly, I'm going to have one more pair of SCR devices connected somewhat like this. This is the second pair, which is connected in B phase. And this is the third pair, which is connected in C phase. So these are the three-phase AC voltage controller. Now, let us say I call this as T1, this as T3, and this as T5, just like how we called it in rectifier case. The same numbering is utilized here also. So this will be T4, this will be T6, and this will be T2. And I'm going to connect loads here. Again, I'm going to show star connected loads. I have not specified whether it is R load or RL load. R load itself is not an easy thing to analyze, so I'm not even going into RL load. So let us try to look at, first of all, three-phase AC voltage controller with resistive load. So let me call this as small n, which is actually the neutral of the load side. Okay. Now let us draw the three-phase voltage waveform. So let me first of all draw, this is A phase. And let me say this is, I'm dividing it into 60-degree intervals. So this is B phase voltage. And I'm going to show this as C phase voltage. Okay. So let us say this is VAN, this is VBN, and this is VCN. And at any instant of time, if I am looking at these AC voltage controller devices being replaced by a diode, it would be sinusoidal, because if I have a diode, it will work during positive half cycle here. Similarly, this diode will work during negative half cycle here. So it is as good as having a simple copper wire connected. So the firing angle in this particular case will be calculated from the point where the devices would have started conducting had they been diodes. So A phase diode would have started conducting right here. B phase diode would have started conducting right here, positive diode. C phase diode would have started conducting right here. So alpha is calculated from VAN or VBN or VCN zero crossing for each of these devices. So if I am assuming that, let us say this is the alpha value, I'm going to calculate alpha like this. So let us say alpha is this, which is equal to 60 degrees. So what I am doing is to fire device number 1 here, device number 2 here, device number 3, and device number 4 here, device number 5, and device number 6 will be fired here, which is also same as firing it here. So this is how we are going to fire. So all the firing of the devices, each of the devices is staggered from each other by 60-degree interval or pi by 3 interval. Now when one is fired, let us say the current is going like this, and it is going to go like this, and if I say 6 was already fired and it is still conducting, I would have the current going like this through B phase. So if 2 is also by chance conducting, the current will divide itself into 2 parts. But if I am talking about only 2 devices conducting at a time, so when I am actually firing 1, if I say 6 and 1 are conducting during this interval, the voltage is going to be VAB. So if I try to look at VAB, VA and VB, they are meeting up here. So VAB will be 0 at this point, exactly at this point. So I should have actually, this point is about at 90 degrees. So VAB would have been somewhat like this. It would have 0 crossing would have occurred here. And I should have had the sinusoid actually going somewhat like this. This is how the sinusoid would be. And then from here, it would go to the other side also like this. This would have been the sinusoid, what I'm talking about in terms of VAB. This would have been VAB. So this point is same as VA and this point is same as VB if we are neglecting the drop across any SCR. So the total voltage that comes between these two, that is going to be VAB. So the voltage across this, if I assume balance load, this will be VAB divided by 2 and this will also be VAB divided by 2. So what I get during this portion, I should show it as though at this point, the voltage will be VAB divided by 2 and it will come down like this. And once 2 is fired, I'm going to have again 1 and 2 conducting simultaneously. So this will be VA and this will be VC. So it will be VAC divided by 2. So this is how the voltage will be. So whenever only 2 devices are conducting, I'm going to have half of the line voltage coming up across every phase of the load. If I'm talking about A phase load, it will be VAB divided by 2 initially for the first 60 degrees, then VAC divided by 2 when 1 and 2 are conducting together. Once 3 is fired, 2 and 3 are going to conduct together, so I will not have any voltage at all coming across A phase. But the moment 4 is conducting, when 3 and 4 are conducting, it will be VAB divided by 2, but VAB will be now negative because already if you look at it, VB is actually greater than VA. So VAB will be negative. So again, you will have something like this coming up. So if I try to draw what is the voltage across, the load corresponding to VA. So if I just say what is VA load, across the load, what is the voltage? Or VAN, if I may call this as this is VAN. So that is going to be, it will jump somewhat like this. And this is going to be the way it is. And then it is going to come down to 0. And then this will be the case as far as A phase load voltage as well as load current is concerned. And this portion is corresponding to 6 and 1 conducting, whereas this portion is corresponding to 1 and 2 conducting. When 2 and 3 are conducting, there is no A phase voltage at all. When we have 3 and 4 conducting, this voltage is going to come up. And when 4 and 5 are conducting, again this voltage is coming up. When 5 and 6 are conducting, nothing is coming. So this is essentially VAB divided by 2. This is going to be VAC divided by 2. This is going to be again VAB divided by 2. That is why it is negative. And this will be VAC divided by 2. So this is corresponding to when we are talking about alpha equal to 60 degree and R load, pure resistive load, pure resistive load. Rather than that, if I had started with, for example, alpha equal to 30 degrees. If alpha equal to 30 degrees, let me draw the waveform once again. I'm going to have this as omega t. And let's say I'm going to have the first phase somewhat like this. And I'm going to divide this into 60-degree intervals somewhat like this. And let's say I'm having the second phase going somewhat like this. And the third phase I'm drawing in gray color, which is also somewhat like this. So this is AN, this is BN, and this is going to be CN. Okay. Now, if let us say I'm talking about alpha equal to 30. So this is where 1 is fired. And if here 1 is fired, I'm going to fire 2 here. I'm going to fire 3 here. I'm going to fire 4 here, 5 here, and 6 here. And again, 1 will be fired there. Now, when I am firing 1 here, I'm assuming that 6 is already fired before, and device number 6 will be able to conduct. Device number 6 is in B phase. It will be able to conduct as long as B is negative. So until this point, 6 will be able to conduct. But you are firing 2 already here. So during this portion between these two, we will have all 3, that is 6, 1, 2, all 3 will conduct. Whereas if I try to look at it here, Before this, 6 must have been fired and 5 must have been fired too. And this is C phase. So actually 5 should be able to conduct until this portion. So we will have again 5, 6, 1 conducting here. During this portion, only 6 and 1 will conduct. And 6, 1, 2 will conduct here. So let me probably circle whatever I have written here. 5, 6, sorry, let me just remove this here. So I can say 5, 6, 1 conduct here during this portion. And 6 and 1 only conduct during this portion. Whereas here it is 6, 1, 2. And before this, it must have been only 5 and 6. And I should be able to say again, for some duration, I'm going to have only 1 and 2. Whereas for again, until here, I'm going to have 1, 2, 3. All three of them conducting together. Okay. So whenever only 5 and 6 are conducting, let me again show the circuit. When you have only 5 and 6 conducting, let me probably show the path again. So when only 5 and 6 are conducting, then what is going to happen is the current will flow like this through 5, through C phase load, then B phase load, and 6, and then return like this. So this is going to be actually, if I try to look at it, I'm going to have basically, this is VC and this is going to be VB. So VCB divided by 2 will appear here. Again, VCB divided by 2 will appear here when 5 and 6 are conducting. So I should be able to say voltage across either VB, if I try to look at it, load voltage, it will be VCB by 2. Maybe it will be somewhat like this. This is VCB by 2. Whereas after that, 5, 6, and 1, all three are conducting. If 5, 6, and 1, all of them are conducting, it is as good as three-phase voltage is applied to the three loads. So VA will appear across this, VB will appear across this, and VC will appear across this. That is how it is going to be, because it is as good as a balanced kind of situation. So when 5, 6, and 1 are conducting, I am going to have voltage across B will be exactly, this is not VB, this will be VCB. Sorry, this will be VC load. Because 5 is conducting, that's why you get a positive voltage. Whereas if I am looking at VC again, VC is still positive. So during this portion, until 5, 6, and 1 are conducting, I'm going to have probably VC appearing. So this is VCN, whereas this will be VCB divided by 2. And it will come down to 0. And after that, when 6 and 1 are conducting, you will not have any voltage at all across C phase. When 6, 1, 2 are conducting, again VC will come into picture and VC is here. It is negative. So it is going to jump to some negative and this is going to be VC. And when 1 and 2 are conducting, it will be AC or VCA divided by 2. So VCA, VC is here, VA is here. So VCA is definitely in the negative direction. So this is going to be VCA by 2. I hope you get the drift of it. Whenever you are having three devices conducting at a time, phase voltage appears across the load. When only two devices conducting. Only when two devices are conducting, during that time, the line voltage, whatever appears across both the loads together, divided by 2. That appears across each of the load. So, if you let us try to look at our simulations once again. I have done some simulation for three-phase AC voltage. First of all, I have started with single-phase AC voltage controller. You can say this is a single-phase AC voltage controller. This is the sinusoidal input voltage, which is VA, and you are looking at wait a minute. Single-phase AC voltage controller, I have already shown. This is the three-phase AC voltage controller. In three-phase AC voltage controller, I have taken only VA. For example, only VA, and I have taken firing angle equal to 60 degrees. When the firing angle is 60 degrees, this is where I am applying the pulse for A phase, and this is the pulse for next phase, B phase. So what happens is whenever A phase pulse is conducting, this current as well as voltage both have to be VAB divided by 2. And when I am actually applying a pulse for device number 2, this is device number 2, which is staggered from the first one by 60 degrees. So at this point, again, VAC by 2 will appear. So this is VAB divided by 2. This is VAC divided by 2. So you can clearly say that during this point, only 6 and 1 will be conducting. Here, 1 and 2 will be conducting. Here, 2 and 3 are conducting. That's why you don't get any load voltage at all. And this is 3 and 4, and this is 4 and 5. So when 3 and 4 are conducting, it is VAB divided by 2. That's why it is appearing to be negative. And this is VAC by 2 again, which is appearing to be negative. So this is for resistive load. The same resistive load, when we are looking at 30-degree firing angle, what we have got, just a second. So here, let me show another waveform with 30-degree firing angle. So when you look at 30-degree firing angle, so you can see that at some point, the output is coinciding with VA. So wherever three devices are conducting, it is coinciding with VA itself. So you can see this is coinciding with VA. Here also it is coinciding with VA. Here it is coinciding with VA. Whereas at some point, it is coinciding with VAB divided by 2. So you can see that VA load, which is in black color, this is VAB divided by 2, whereas you are going to have at some point it is VAC divided by 2. So in certain portions, you can see VAB divided by 2 coming up. In certain portions, you can see VAC divided by 2. Again, here it it is same as green color, which is VAB divided by 2. And at this point, the blue color, which is VAC divided by 2. So whenever you're going to have the firing angle to be very, very small, very low, under such a condition, you would see normally line voltage and phase voltages appear alternately across the load voltage waveform. Whereas whenever you are talking about larger firing angle, under such a condition, you would see normally that the voltage that is appearing across the load will be mainly line voltage divided by 2. And that's what we saw in the previous case. We saw that when the firing angle was 60 degrees, in this particular case, we never see the pink voltage appearing, magenta voltage appearing across the load at all. Black color is the load voltage waveform. You can very clearly say initially it is VAB divided by 2. And after that, it is VAC divided by 2. VAC is blue color. So this is VAC divided by 2 during this portion. And similarly, this is VAB divided by 2. And this is VAC divided by 2. After all, because the load, we have assumed it to be resistive, we are not going to have any variation between the current voltage wave shape and voltage current waveform and voltage waveform. The shape will be exactly similar. Only thing is voltage divided by the resistance will be current. That's all. So I have not even plotted the current. Maybe I have plotted. Let me show the current waveform. Yeah, this is the current waveform. You can see this is the voltage waveform, which is black in color. And this is the current waveform, which is red in color. Both of them are exactly similar in terms of their shape. Only they are scalar multiple of each other. There is a scalar multiplication between the voltage and current. Before we conclude on the AC voltage controller, I would like to highlight only one point. If the resistive load itself could be so complicated in terms of some line voltage appearing and some phase voltage appearing in between, it is not going to be all that easy to analyze it with an inductive load. If we try to analyze it with an inductive load, what will happen is the current would not finish itself right here. So I may have a current actually slowly increasing like this. It might increase like this. The current might increase like this. And beyond a particular point, it will start coming down. And again, I may have the current increasing like this and it may come down, but it will not come down at this point. It will continue like this. So I may have a current waveform somewhat like this and it will come down like this. And I may have again the current appearing like this and so on. So the thing is, the inductive load waveform becomes much more difficult to kind of analyze and, arrive at exact values. So unless we do the simulation for R and L load, it's very difficult to say where phase voltage will appear, where line voltage will appear, how long it is going to continue. These things cannot be said very easily. Of course, in this particular case, the current has to reach zero, and only after that, the current has to reach zero and there should be a small dead period, and after that, the current has to start once again. So it's very difficult to analyze with inductive load in the case of a three-phase AC voltage controller. And before concluding, one more thing I want to say is, if let us say I want the current to flow in a resistive load in the case of a three-phase AC voltage controller, in that case, I have to have at least some overlap between one positive device and one negative device. So if I am looking at this as VAN and this as VBN, the negative device corresponding to VBN is 6, device number 6. And that can continue to conduct only until this point. It cannot conduct beyond this point. So only if VAB is positive, I'll be able to get a current between A phase and B phase. That is, the current will go from A phase through device number 1, and it can return through B phase with device number 6. The current will be able to return through device number 6 and it can flow through device number 1 only if I have this is VA and this is VB, only if VAB is positive. If VAB is not positive, it will not be able to, these two devices will not be able to join hands and conduct. And VAB will be positive until this point only, not beyond this point. And that corresponds to omega t equal to 150 degrees. This is where omega t is 150 degrees. So I should say theoretically for a three-phase AC voltage controller with R load, with the resistive load, maximum firing angle, alpha maximum can be only 150 degrees. If you try to fire it beyond 150 degrees, VAB, they are not going to join hands with each other to pass a current through the load, so it will not work at all. So for a resistive load, in a three-phase AC voltage controller, the star-connected three-phase AC voltage controller configuration, what I have shown just now, the maximum firing angle could be only 150 degrees. And we are not going to analyze the three-phase AC voltage controller much with RL load. If at all you are interested, you can do some simulations and check it out as to how the waveforms are coming. Otherwise, we are going to stop with respect to AC voltage controller at this point, and we will start on DC to DC converters in the next class. And in DC to DC converters, we will be looking at the basic non-isolated converters like buck, boost, and buck boost, and probably Chuk converter, CUK, Chuk converter also in the next class. But we will be looking at isolated converter in terms of flyback, half bridge, full bridge, and dual active bridge converter.